Out in the wilderness, the administrator finds a broken robot. Its internal repair interface is a 4x4 Originium circuit panel. There are tally marks around the edge. You can read them as numbers. They tell us how many positions in each row and each column should be connected. The administrator tries fitting her Tetris-like blocks for a while, but nothing lines up. Then she starts to wonder, what if the problem is not her repair skill, but the requirements themselves? Forget the complicated shapes for a moment. Let's simplify the problem. Suppose I only have one cell blocks. Can I fill the board, abstract it one step further? Turn placing blocks into filling in numbers. Each cell contains either 0 or 1. A1 means this position is connected. A 0 means it is not then. All we need is for every row and column sum to match the requirements. The original shape of the circuit board no longer matters. All we need is a table of numbers. Let's give this table a name. Let's call it a matrix. So the repair interface becomes a 0-1 matrix. The side numbers are the required counts of ones in each row and column. Let's start with a small example. In this little matrix, the first row has 2 ones, the second and third have 1 each. So the row sums are 2, 1, 1. Counting by columns gives 2, 1, 1 as well. This is one filling pattern that satisfies the requirements. But the administrator soon notices there is another way to view the same thing. Let each row correspond to a vertex. Let each column correspond to a vertex too. Whenever a cell is filled with a 1, draw an edge between the corresponding row vertex and column vertex. The graph we get has its own name, a bipartite graph. Its edges only go from left side vertices to right side vertices. There are no edges inside the left side or inside the right side. The number of edges incident to a vertex is its degree. So a row sum in the matrix becomes a left side vertex degree, and a column sum becomes a right side vertex degree. The repair puzzle has become a graph theory problem. Given 2 lists of numbers, one for each side, can we draw a simple bipartite graph whose vertex degrees are exactly those numbers? This is the bipartite graph realization problem. Mathematicians Gale and Reiser give a classic criterion. We do not need the full theorem right away. Let's use this example to see the logic behind it. The panel now requires row sums 4, 4, 1, 1. The column sums are 3, 3, 3, 1. First, the total counts match. On the row side, 4 plus 4 plus 1 plus 1 equals 10. On the column side, 3 plus 3 plus 3 plus 1 also equals 10. The real problem appears in the first 3 columns. Each of those columns needs 3 ones, so together they need 9. But those 9 ones have to come from 4 rows. Let's see how many the rows can supply in the first 3 columns. The first row needs 4 ones in total, but only has 3 positions there. So in those columns, the first row can supply at most 3 ones. The second row is the same. It can also supply at most 3. The third row only needs 1 in total, so it can supply at most 1 there. The fourth row also supplies at most 1. Altogether, the maximum is 3 plus 3 plus 1 plus 1, which is 8. But the first 3 columns need 9. 9 is greater than 8, contradiction. So these requirements were impossible from the start. In other words, this repair interface really is mislabeled. That idea is the key to the Gale-Reiser criterion. First, the totals must be equal here. Sort the column sums in non-increasing order. The column sums 3, 3, 3, 1 are already sorted then. Check every prefix of the columns. Can the rows provide enough ones for that prefix? For example, the first 2 columns need 6 ones in total. The 4 rows can supply at most 2 plus 2 plus 1 plus 1, which is 6. So that prefix works. But for the first 3 columns, our earlier calculation shows the rows cannot supply enough. So this set of requirements is not realizable. In general, these are the 2 conditions above. They may look complicated, but the logic is exactly what we just used. If we change the row sums to 4, 4, 2, 1 and the column sums to 3, 3, 3, 2, the contradiction disappears. After checking, this requirement set is realizable. Now we get the next question. Once we know a realization exists, how do we construct one? The administrator thinks of a very direct method. The test is really telling us to prioritize the columns that need ones most at each step. Give as many ones as possible where the demand is highest. Inspired by that, we can place the ones in each row into the columns that need them most. Call this the greedy repair algorithm. Handle the first row, then the second, and continue row by row. For example, the row sums are 3, 2, 1, the column sums are 2, 2, 1, 1. The first row needs 3 ones, so choose the 3 columns with the largest remaining demand. If there is a tie, choose any of them. Here, say we choose columns 1, 2, and 3. After filling the first row, those 3 column demands drop by 1. The remaining demands become 1, 1, 0, 1. The second row needs 2 ones. Again, choose the 2 columns with the largest demand. Here, choose columns 1 and 2. After filling them, the demands become 0, 0, 0, 1. The third row needs 1, 1, so it must go in column 4. Now we have a complete 0, 1 matrix. Its row sums are 3, 2, 1, and its column sums are 2, 2, 1, 1. So the greedy algorithm really found a valid fit. But why can't the greedy algorithm construct a valid solution? Could it get stuck in a contradiction at the end? In fact, one can prove that if any solution exists, then there is also a solution that follows the greedy repair rule. The key is an adjustment operation. Start from any solution, then gradually adjust it into one that follows the greedy repair rule. Notice that this kind of 2x2 switch does not change the row sums or column sums. So after the switch, we still have a solution. Do several of these 2x2 switches, and we can obtain a solution satisfying the requirements. Suppose there are 2 columns and the left one needs a 1 more urgently than the right one. But in the first row, the left entry is 0 and the right entry is 1. Then, that one is not where the greedy repair rule wants it. Since the left column's total demand is at least the right column's, some lower row must contain the opposite pattern. Left entry 1, right entry 0. Now we can switch this 2x2 block. Change 0, 1, 1, 0 into 1, 0, 0, 1. After the switch, every row has the same number of ones. Every column also has the same number of ones, but the first row one has moved to the place that needs it more. So whenever a filling exists, we can use switches like this to arrange the first row the way the greedy rule wants. After the first row is arranged, fix it and remove it. What remains is a smaller problem of the same kind. Then the administrator can keep repairing row by row. Math can decide whether a solution exists and also show a way to find one. Looking back, we used 3 ideas. The Gale-Reiser criterion tells us which requirements are impossible from the start. The greedy repair algorithm tells us how to fill the matrix step by step when it is realizable. And the 2x2 switch explains why. If a solution exists, the greedy method can also find one. Of course, the original puzzle is more complex than this 0-1 matrix model. Math will not place every module for the administrator automatically, but it tells her something important, which requirements are impossible and which are worth trying further. Maybe knowing a little graph theory really does make a better administrator. If you enjoy this kind of video, finding math in games and everyday life, please subscribe to the channel. If you have a small math question, leave it in the comments. I may pick some good ones and explore them in future videos. If this episode helped you, please like it and share it. See you next time.